So, hello, welcome to the class. So, we will be continuing with series. Okay. So, for a sequence AN, okay, an infinite series is defined as summation n going from 1 to infinity AN. Okay. Now, let Sn is equal to A1 plus A2 till AN. Okay. The series sigma n going from 1 to infinity AN converges if and only if this particular sequence Sn converges. Till this we have done in series. So from where a series is made? A series is made from an infinite sequence. Okay. Then we will always talk about infinite series and how do we define convergence or divergence of a sequence. This a series is said to be convergent if and only if its sequence of partial sum converges. Okay. So today we are going to discuss ways in which we can check whether a particular series is convergent or not. Okay. So the first thing that is used to check whether a series is convergent or not is the necessary condition. Okay. So what is the necessary condition? The necessary condition says if sigma n going from 1 to infinity an is convergent, then limit n tending to infinity an should be equal to 0. This is a very important condition. If at all the series is convergent, then the limit of an as n tending to infinity should be 0. But the converse is not true. Converse is not true. What does it mean? It means limit n tending to infinity an equals to 0 may or may not imply that sigma n going from 1 to infinity an converges. Okay. So if at all the series converges, then the limit as n goes to infinity an has to be equal to 0. For example, if you get this question, sigma n going from 1 to infinity, n square upon n square plus 1. For example, this is your series. Okay. The first step which you should check is what is an? What is the general term of the series? So the general term of the series over here is n square upon n square plus 1. Okay. So we can write it as n square divided by n square divided by n square plus 1 divided by n square. So an is nothing but 1 plus 1 upon n square. So limit n tending to infinity an is equal to 1. Now, since this limit is not equals to 0, we can say that sigma n going from 1 to infinity n square upon n square plus 1 is not convergent. Now, this is the beauty of this test. So, whenever you are asked to check the convergence of a series, always check where this limit is going. If this limit is non-zero, you can straight away say that this is not convergent. If this limit is 0, then we are going to proceed with our tests for the convergence or divergence of a series. Is it clear, everybody? Any doubt till here? The first thing is that if the series is convergent, then limit n tending to infinity an has to be 0. Therefore, if limit is not 0, it will automatically imply that the series is not convergent. Are we clear till here? Suppose you're given this series. So now, if you look at an is equal to cos of n. And limit n tending to infinity cos of n doesn't exist. Okay, this limit will never exist because cos oscillates between -1 and 1, and we don't know what happens when n goes to infinity. Cos is a bounded function. It is not going to a fixed value as n is approaching infinity, because cos is oscillating between +1 and -1. Okay. So this test is very handy in checking the convergence or divergence of a sequence. In fact, if you need to prove that the sequence is not convergent, the first test that you should think of is this test. You should calculate limit n tending to infinity an. Okay. Now we have another ways to check the convergence of a sequence. So suppose sigma n going from 1 to infinity an is a series, okay, such that an is positive. So suppose you have a positive term series. There are no terms in the series which are not positive. Okay. It is a positive term series and it doesn't even have zeros. Okay. So we will be introducing a ratio test. Okay. So let us talk about this limit. Limit n tending to infinity an plus 1 upon an. So we will be talking about this limit. If this limit, suppose this limit is L. Okay. If limit L is less than 1, the series is convergent. Okay. If the limit is greater than 1, the series is divergent. And if limit L is equal to 1, test fails. What do you mean by test fails? That means we cannot conclude anything with the help of the ratio test. So ratio test is very, very useful when we have a limit L less than 1 or greater than 1, because L less than 1 implies that the series is convergent. L greater than 1 implies that the series is divergent. So this is a ratio test. Okay. And let's see whether we can have some questions related to this. Okay. Okay. So let us see. Okay. For example, if you look at practice question 2, okay, practice question 2, question number 1, if you see, let us look at A. For each of the following series, determine whether it converges. If so, find the sum. Okay. So let us look at this series, sigma n going from 1 to infinity 2 power n, 3 power n minus 1. So if you look at this series here, an is 2 power n divided by 3 power n minus 1. Okay. So if you look at an plus 1, it will be 2 power n plus 1 divided by 3 power n plus 1 minus 1, which is 2 power n into 2 divided by 3 power n. Now this is gone. So this is 3 power n minus 1 into 3. So an plus 1 equals to 2 by 3. And if you look at this is an. So an plus 1 upon an is 2 by 3. So limit n tending to infinity, an plus 1 divided by an is nothing but 2 by 3, which is less than 1. Hence, this is a convergent series. So if in this question you are asked, check whether the series is convergent or not, just check this ratio. An plus 1 divided by an, calculate the limit. If the limit is less than 1, it is convergent, greater than 1, divergent. Now, in this case, you have to find out the sum also. Now, to find out the sum, we have to come to a very nice result. Okay. So, we all know about geometric series. Okay. So from now onwards, you should try to observe what is a geometric series. A geometric series takes this form. Limit n going from 1 to infinity, a r n. You all know this. So this is a, or so, we can start with this. Okay. So when n is 1, you get a, then n is 2, you get ar square, and so on. Okay. Now a geometric series is convergent. Okay, if and only if the absolute value of r is less than 1. We have also done this result. Okay, so a geometric series is convergent if and only if the common ratio lies between -1 and 1. इसका ये मतलब होता है. Okay, so what is the sum? In that case, the sum will be A upon 1 minus R. Okay. Now let us try to look at this series. So sigma n going from 1 to infinity, 2 power n, 3 power n minus 1. So we can write it as sigma n going from 1 to infinity. We can have this as 2 power n minus 1, 3 power n minus 1. So this is summation n going from 1 to infinity 2. This is 2 upon 3 power n minus 1. So this is actually nothing but a geometric series. You can see that it is of this particular form, a into r raised to the power n minus 1. Now in this particular case, a is 2 and r is 2 by 3. So what should be the sum of the series? A upon 1 minus r. So which is 2 upon 1 minus 2 by 3, which is 2 upon 1 by 3, which is 6. So in this case, the sum of the series is coming out to be 6. This is the beauty of the ratio test. So for ratio test is also useful when we have factorials in place. For example, here we have state and prove divergence and convergence for each of the following series. So here we do not have to find the sum. Finding the sum is not easy in all the cases. Okay. So let us look at this. If you look at this, summation n going from 1 to infinity, 3 power n factorial divided by n power n. Let us see what happens over here. Okay. So again, if you look at this, here this is your an and your an is positive. There is no negative sign involved. So your an is 3 power n factorial, n power n. So your an plus 1 would be 3 power n plus 1, n plus 1 factorial, n plus 1 power n plus 1. Okay, let us see. This seems very interesting. So an plus 1 upon an is 3 power n plus 1, n plus 1 factorial divided by n plus 1 power n plus 1 whole divided by 3n, n factorial, n power n. So if we simplify this, so we will be having this 3 will be in the numerator, and then we have n plus 1 factorial, and this is n factorial. So we will have n plus 1 in the numerator, and then we will have n by n and n plus 1 power n plus 1. I hope I'm correct. Okay. So this is 3 n plus 1 n by n divided by n plus 1 n plus 1 power n. So this is 3, and this is we can write it as n upon n plus 1 whole power n. So this is 3, and we can write it as 1 plus 1 upon n whole power n. And this is 3 divided by 1 plus 1 by n whole power n. So now if I calculate limit n tending to infinity, an plus 1 upon an, this is going to be a limit n tending to infinity, 3 upon 1 plus 1 upon whole power n. This is 3 into limit n tending to infinity, 1 upon 1 by n whole power n. Now this is a very, very famous limit. Limit n tending to infinity, 1 plus 1 by n whole power n is e. Okay. So this is going to be 3 into 1 upon e. So my limit is 3 by e. Now your e is approximately 2.73, something like this. So therefore your 3 by e will be greater than 1, and therefore this particular series is divergent. So that is the beauty of ratio test. Especially in ISI, you are given 3-4 series and you have to check which of the series are convergent or divergent. And in those cases, these ratio tests becomes very handy. So whenever you see factorials and whenever you see a pattern of the geometric series, ratio test becomes very, very useful. So now we discuss another test which is known as a direct comparison tests. Okay. So as the name suggests, direct comparison test, what is it? So if sigma an, n going from 1 to infinity. Now I am again and again writing n going from 1 to infinity. You can even miss that part because it's not very important, it's obvious. So if sigma an and sigma bn are two positive termed series, okay, such that an is less than or equal to bn for all n, okay. So if each term of this series is less than or equal to the corresponding term of this series, then case 1, if sigma n going from 1 to infinity bn converges, then sigma n going from 1 to infinity an converges to. And it is very easy to observe. You can see that an is less than or equal to bn. Iska matlab, when we talk about the sum will also be should be less than or equal to the sum of bn. Okay. Therefore, this series, if at all it has a sum, its sum has to be less than or equal to the sum of this series. Now, if this series is convergent, it means this series has a sum, and therefore this series will also converge. So if I have a bigger convergent series, okay, and I have a smaller convergent series than this bigger convergent series, then the smaller series will converge too. It cannot diverge. Okay. And if you want to talk about divergence, so if the smaller series diverges, that means if n going from 1 to infinity, an diverges, then sigma n going from 1 to infinity, bn diverges too. Okay. So this is called direct comparison test. Sometimes by observing only, you can see, like for example, sometimes you'll not be able to apply ratio test. So, in those cases, direct comparison tests becomes very, very useful. Okay. So to use the direct comparison test, you should be knowing some particular types of series. Okay. So first of all, we already know about geometric series. Okay. So geometric series we already know. So any series of this type, a Rn minus 1 converges to a upon 1 minus r if and only if minus 1 is less than r is less than 1. Then there is something known as P series, and this is a standard result. So we do not need any proofs for that. These series are very handy. So any series of this type is called a P series. Okay. So there is a test which is known as P series test, or we can say that, so P series converges. So there is no third arrow. There are only two cases. So a P series converges if P is greater than 1 and diverges if P is less than or equal to 1. And this particular series, when P equals to 1, this particular series is 1 upon n. So this is 1 upon 1 plus 2 upon 1 plus 3. This is called a harmonic series. Okay. And a harmonic series is divergent because here P is equal to 1. Okay. So geometric series is very useful, as whenever we have, something called a direct comparison test, they will come very handy. And P series, sometimes you just see P series and you'll come to know that you'll be able to compare a series with a P series and you'll come to know whether it converges or diverges. Okay. Okay, let us try to look at this series of the type C, F, and let us see whether we can apply some test over here. So you have n going from 1 to infinity, n root n divided by n plus 3 whole cube. Okay. So now let us consider this as an. So an is n root n divided by n plus 3 whole cube. So we know that n is a natural number. So therefore, n is less than n plus 3. So n cube is less than n plus 3 whole cube. And if we take the reciprocal, this is greater than this. So this will imply, okay. And then if we take n root n, this is n root n divided by n cube. So what we notice is that your an is less than n root n. What is n root n? N power 3 by 2 divided by n by 3. So your a is less than 1 upon. So your an is less than 1 upon n power 3 by 2. Call it bn. Okay. So basically now I have found out a series with which I can compare this series. And I found a useful series because I know about this series. This is a P series. So if we talk about sigma bn, n going from 1 to infinity, this is nothing but n going from 1 to infinity 1 upon 3 n power 3 by 2. And this is converges because here the power which is P, which is 3 by 2, it is greater than 1. And I told you in the direct comparison test, if the bigger series converges, the smaller series converges too. So you can see that this particular series is going to be smaller than this series. And this series is convergent. Therefore, by direct comparison test, this particular series converges. Okay. Okay, so now let us try to look at this particular series. Summation n going from 1 to infinity, n plus 2 upon n root n, which I can write as summation n going from infinity, n upon n root n plus 2 upon n root n. See, I can talk about sum of series also. If there are two series, okay, if we're adding two series, if both are convergent, the sum is convergent. If both are divergent, the sum is divergent. But if one is convergent, one is divergent, the sum is divergent. Okay, so let us see. So now we can write it as n upon n root n plus n going from 1 to infinity. This 2 can be taken out. When I'm doing these calculations, if you do not understand anything, please ask me. I think it's quite simple. So I can write it at like this. Okay. And so you see, this is another beautiful application of the P series. Because if you look at this P series, this series is convergent. And if you look at this wonderful series, this is divergent. Just by looking at the powers. Here the power is greater than 1 convergent. Here the power is less than 1 divergent. So this series diverges. Okay. Here is a convergent series. Here is a divergent series. Divergent series. So here we've dealt with sum of two series. Okay. Now, let us try to look at this particular series. This. Okay. So we have summation n going from 1 to infinity, natural log of n plus 1 divided by n. So if you look at an, it is, okay, this series requires some smart work. Okay, so this is my an. So if I look at, Sn, what is Sn? A1 plus A2 plus A3 plus A4 plus A5 plus An. Okay, the sequence of partial sums. So if you look at this, let's see how it looks like. So when I put n equals to 1, I'll get log 2 minus log 1. If I put n equals to 2, I'll get log 3 minus log 2. Then I'll get log 4 minus log 3 plus log 5 minus log 4 and so on. And the last term would be log n plus 1 minus log n. So if you see, I'll cut this with this, then I'll cut this with this, I'll cut this with this. So eventually we are going to be left with, let us see what is the penultimate term before this to have clarity. Okay. इससे पहली वाली टर्म भी लिख लेते हैं. So we should be having yeah. Okay. So yes, this will get cancelled out with this. So eventually your Sn will be log n plus 1 minus log 1. So your Sn will be log n plus 1 minus 0. Log of 1 is 0. So if you see your Sn is this, and I told you that the series converges if and only if this limit exists. So let us look at the limit of sequence of partial sum. Here is a question where sequence of partial sums is coming into play. So as n tends to infinity, log is an increasing function. Okay. So as n becomes large and large, this becomes large. So this becomes plus infinity. So therefore, this particular series is divergent. Okay, it is diverging to plus infinity. So this is the beauty of sequence of partial sums. Okay, this question very smartly we could find out the nth term because the subsequent terms were cancelling out with each other, and we could see that the sequence of partial sum is going towards plus infinity, and therefore my series will also go towards plus infinity. It is not going to converge. It is in fact going to diverge towards plus infinity. N going from 1 to infinity, 1 minus 1 upon n power n. Okay, this should be plus. Okay. Now, if you look at the an over here, an is 1 plus 1 upon n whole power n. Okay. So if you talk about limit n tending to infinity an, it is limit n tending to infinity 1 plus 1 upon n power n, and this is e. We discussed it one more time before this question. This limit is e. So I already told you, if this limit is not equals to 0, this given series is not convergent. In fact, divergent. Okay. So this is the beauty of the nth term test or the divergence test, the first test which we had discussed today. Okay. If you look at the second series, summation n going from 1 to infinity, 1 upon 3 power n plus 1 upon 4 power n. So this is some n going from 1 to infinity. I can write it at this plus n going from 1 to infinity, 1 upon 4 power n. So you can see that this is a geometric series. 1 plus 1, 1 upon 3 plus 1 upon 3 square and so on. This is a geometric series, 1 upon 1 by 4 plus 1 upon by 4 square and so on. And here a is equal to 1 by 3, here r is equal to 1 by 3. A equals to 1 by 4, R equals to 1 by 4. In both the cases, the common ratio is less than 1. The absolute value is less than 1. So this series is convergent. This series is convergent. Sum of two convergent series is convergent. This is convergent. And what is the limit? Calculate the sum. A upon 1 minus R. Calculate the sum. A upon 1 minus R. So 1 upon 3 divided by 2 by 3. 1 upon 4 divided by 3 by 4. So this is half plus 1 by 3. Okay. So simple questions. Then find the formula for the nth partial sum of log n upon n plus 1. We did a question like this. Exact question like this. Just that we had n plus 1 in the numerator. So this question can be tried. Sigma n going from 1 to infinity 1 upon, this is called a harmonic series. This is divergent by P series test. I've already told you that, this is going to be a divergent series if P is equal to 1. So these are simple questions for your practice. So let's talk about binomial expansion. So if n is a natural number and we have a plus b power n, we can write this as nc0 a power n b power 0 plus nc1 a power n minus 1 b power 1 plus nc2 a power n minus 2 b power 2 plus nc3 a power n minus 3 b power 3 till ncn a power 0 b power n. This is the formula for binomial expansion. In the formula for binomial expansion, what do you mean by NCR? It is n factorial divided by n minus r factorial into r factorial. The conceptual meaning is choosing r things out of n things. इसका ये मतलब होता है. So suppose you have to deal with a plus b power 100. So this formula will be very useful. Of course, nobody is going to ask you that please expand a plus b power 100 because that's going to be an utter nonsense. But they might ask you, what is the 17th term? How does the 17th term look like? So you notice one thing. If you look at the first term, in the first term, I have 0. Okay. In the second term, I have 1. In the third term, I have 2. ये देखिए. In the fourth term, I have 3. Okay. So suppose somebody wants to find out r plus 1th term. So I am going to have 1 less than r plus 1. Okay. So n c r a power n minus r b power r. So this is the formula for r plus 1th term in the binomial expansion. Okay. So binomial expansion, whenever we talk about, the general concept is the rth term or the r plus 1th term. Nobody is going to ask you the expansion. Okay. For example, if you, let's try to. Okay. Now, if you look at this question, if the coefficient, now this came in ISI 2011, if the coefficient of 2r plus 5th and the r minus 6th term in the expansion of 1 plus x power 39 are equal, then what is RC12? So first of all, you have 1 plus x power 39. Okay. So if you look at the formula for T 2r plus 5, okay, 2r plus 5, it is going to be 39c 2r plus 5. In fact, it has to be 1 less. Okay. And then x power. Now, what is a plus b power? If we have 1 plus x power n, it will be nc0. You can start with, x power 0, 1 power n. Then nc1, x power 1, 1 power n minus 1. Because all the powers of 1 are same. nc2, x power 2, 1 power n minus 2, and so on. So in this case, the power of x will be 2. Okay. So whatever is here, 2r plus 4. All right. So what is the coefficient here? The coefficient is equal to 39c 2r plus 4. Now r minus 6 term. So that means tr minus 6. So if I talk about tr minus 6, I will have 39c r minus 7, 1 less, and then x whole to the power r minus 7. So what is the coefficient here? 39c r minus 7. This is the coefficient. What is coefficient which is not involving the variable? What is the variable here? The variable is x here. So I have to get rid of the coefficients. I have to get rid of the variables. So now the coefficients are equal. So it is given that 39c 2r plus 4 is equal to 39 CR minus 7. Okay. Now we have to find out the value of RC12. So if these two are equal, now if NCR is equal to NCP, then either R equals to P or R plus P equals to N. This is very important. This is a standard result. So now if these two are equal, I should have 2R plus 4 is equal to R minus 7, or 2R plus 4 plus R minus 7 equals to 39. यहां से R की वैल्यू -11 होगी, which is impossible. Why? Because I am choosing, I cannot choose negative things, because if R is -11, it is going to be -11 C12, which is not making sense. I cannot choose 12 things out of -11 things. The number of things cannot be negative. Now let us look at this. This is going to be 3R minus 3 equals to 39. So 3R equals to 42. So R is coming out to be 14. So let us calculate RC12, which is 14C12, which is 14 factorial divided by 14 minus 12 factorial divided by 12 factorial. So 14 factorial, 2 factorial, 12 factorial. So 14 into 13 into 12 factorial divided by 2 factorial into 12 factorial. This and this will get cancelled out. 2 factorial is 2. 2 times 7, 13 sevens are 91. Option number B is the correct answer. So as far as binomial expansion is concerned, there they do not want you to expand. Okay, they do not, because you see the power is 39 here. Nobody is interested in knowing in the expansion in detail. What they will trick you with is that they will ask you to find the coefficient of a particular term, and then they will say this coefficient is equal to the coefficient of some other term, and then they will tell you to find out something as asked in this particular question. Okay, so you should know the formula for binomial expansion. You should know how to deal with the questions related to binomial expansion, and so on. So the coefficients are equal. So basically coefficient of T 2R plus 5 is equal to coefficient of T R minus 6. Now the coefficient of T 2R plus 5 is NC. Now यहाँ पर R plus 1 है, यहाँ R होगा. So we have 2R plus 5 here, so we will have 2R plus 4. X power 2R plus 4 equals to coefficient of TR minus 6. So NCR minus 7 X power R minus 7. So from both the sides, we have to equate the coefficients. We are not interested in X. So this is the coefficient. This is the coefficient. So NC 2R plus 4 is equal to NCR minus 7. This is what we have got. After that, we have a standard result that NCP is equal to NCR if and only if N is equal to P plus R or P is equal to R. There are only these two conditions. So when we put this equal to this, we get a contradiction. So what we get is this 2R plus 4 plus R minus 7 is N. And what was my N here? 39. So 3R minus 3 is equal to 39. So 3R equals to 42. So R equals to 14. That is what I got. Okay. So when I got R equals to 14, then I put R equals to 14 here. So I calculated 14C12 and it came out to be 91.